That is volume flux. Let's now talk about electric flux. This is just an analogy for what we really want to talk about. Electric flux. And electric flux is defined this way. And here's the symbol for it. This is a phi or a phi. Some argument, is it phi or phi? Well, it rhymes with pi. In terms of the circumference is 2 pi r. If you're talking in Greek, you actually say pi. But I think people are too embarrassed to keep saying p all the time. So we call it pi. And that is so you can call it a phi or a phi. Either one is good. Phi or phi with a subscript e, that is the symbol for electric flux. And electric flux is equal to or defined as E dotted on A, or EA cosine theta, where theta is the angle between E and A. Theta is the angle between E vector and A vector. Now, this is true only for uniform electric fields. How would I draw a uniform E field if I'm using field lines? You want it to be evenly spaced like that. Here's the area that it's all cutting through. This A vector would be something like this. I'll put my A vector with yet another color. A vector would be perpendicular to this thing. That's the A vector. And here is my, if any of these are an E field vector, this angle right here is theta right there. If these are the E field vectors and that is an A vector, the angle is right there. So for uniform E fields, it's pretty easy. It's just E dotted on A is the electric flux, or phi sub E is the electric flux. It's a little bit more complicated. What do you suppose we're going to have to do if we have a non-uniform electric field? Integrate is correct. Here is the general statement for, this works for all fields, all E fields. You can do this, whether uniform or not. The electric flux will be equal to the integral of E dotted on dA vector. And that is what that means is, let's say we have a weird kind of shape here that we're going through, and maybe it's just, I don't know what it looks like, it's just some kind of weird shape. We have our field, and who knows what the field looks like. I'll use a different color for the field. Field going through like this, and it may not be uniform. In other words, it might go in different directions. It may have different weaknesses, different strengths, and maybe it's like weaker over here because it's farther apart. Those are the E field lines. And the dA vector would be something like this. Here's our little dA vector, like that. I'll draw that vector right there. dA, little teeny piece of area, which is always perpendicular at that point. What is the length of the dA vector? Infinitesimal. It is infinitesimally small, but when we add up the E's, all these E fields, times the little dA vectors, we will get something that is finite.